Capacitance of a polar plate capacitor with dielectric slab between the plates. Okay, so this topic is actually very important, and there is one question also which has come from this topic in this year 2021, and it asks you to find out the capacitance of a polar plate capacitor when a dielectric slab is introduced between the plates of the capacitor. So here we are considering that two polar plates here, positive and negative plate, each having a charge q, and the area of each plate here, it is capital A, and the surface charge density of this plate, let's say it is sigma. All right, okay. The distance between the plate here, it is small d, and this plate will create an electric field E naught which is acting in this direction. All right, now when we introduce a dielectric between the plates, then what happened? We have seen in the previous video that there will be an induced field inside the dielectric field, and that induced field, it is EP, and this EP, it is acting opposite to the applied field E naught. So because of this opposite electric field EP inside the dielectric, so therefore the applied electric field E naught, right, will reduce, and that reduced field inside the dielectric slab, it is E, and therefore this E, right, it is equals to how much? E naught minus EP, and the directions of this E, it is acting along the directions of E naught. Okay, so we also have seen, right, that the capacitance of an air capacitor, that means when there is no dielectric, the capacitance of the polar plate capacitor is equals to this much, C naught equal epsilon naught A upon D. Also the electric field between the plates of an air capacitor, E naught equals sigma upon epsilon naught, but sigma is nothing but charge present per unit area, okay, times epsilon naught, right? So these are the things that you have learned in the in the previous videos. Okay, so now we also have seen before that this dielectric constant or relative permittivity, it is equals to the ratio between the applied field to the reduced field E. I can say here E is equals to E naught by K, right? Okay, so these are the equations which are needed here. All right, okay. Now the introductions of this dielectric slab, okay, will change the electric potential, okay, the electric potential differences between the two plates. Before, when there is no dielectric slab, the electric potential between the two plates, it is V naught. But when you introduce a dielectric slab, then the electric potential difference between the two plates changes to V. And as you know, V is equals to electric field times the distance between the plate. So in this case, I will write V is equals to, what is the electric field? There are two electric fields here actually. One is E, another is E naught. So this E naught, it is acting over which distance now? Now this E naught, it is acting only on this free space. Okay, so when I say free space, mean the distance, right, of this free space, it is d minus t. So therefore electric field E naught, it is acting over a distance d minus t times the plus the electric field E, it is acting over which distance? Small t, so plus et. Okay, or V here is equals to E naught d minus t. Instead of small e, I will write E naught by K, and then T. Next, I will take common this E naught. Inside you will have only d minus t plus T upon K. So this is the electric potential. Okay, or V is equals to E naught. What is E naught? Look at equation 1. Q by E epsilon naught times d minus t, right, plus T upon K. Okay. Okay. Now our aim here is to find out the capacitance of the parallel plate. So therefore the capacitance of the parallel plates when the dielectric slab here is introduced between the plate, it is denoted by Cm, and as you know, this C capacitance is equals to Q upon V, or Cm here is equals to, instead of V, if you substitute this value, then you'll get Q upon A epsilon naught D minus T plus T upon K. Or you can say here that this electric capacitance, cancel this, you'll get A epsilon naught upon D minus T plus T upon K. So this is the required expressions for the electric capacitance of a parallel plate capacitor when a dielectric slab is introduced between the plates. Okay. Okay. Now suppose this is my equation 3. Now my special case here is that if this whole space between the dielectric, let's say it is filled completely, if this whole space between the two parallel plate, let's say it is filled completely with the dielectric, then when the space is completely filled with the dielectric, then just look at this small t here. Now it will become this much, which means it is equivalent to small d. So when the whole space is filled with the dielectric, then small t is equals to d. T is equals to d, right? So when t is equals to d, then your Cm here is equals to A epsilon naught. Now because these two are equal, you'll have only just T upon K. Alright, or I can say that, okay, even this, instead of T also I'll write D. So this Cm is equals to, take this K up, it becomes K A epsilon naught upon D, or Cm here is equals to K. What is this? A epsilon naught upon D. This is nothing but it is the capacitance of an air capacitor. So please note down this equation, which is also important when the question asks you to show that the capacitance of when the space is filled with the dielectric is equals to K times the air capacitor. So this is how you have to show. So till here, I hope you are clear with this topic, and please be careful, right? You have to study well about this topic, because this year also, right, a question has come from this topic. So I don't know whether next year they will be asking you about this topic or not, but just prepare well about this topic. Thank you.